You may get a consent to the stream. I think we're live. Except I don't see your video anymore. Oh, yes. I don't see your video anymore. Oh, yes. Not sure what it is. Well, I'll just remove the videos. Okay, go ahead and get started. So we're here doing.
So does the audio work?
Okay.
Yeah, I guess it does. Yeah.
Okay. I think it's gone.
Okay. So let's see. Is my screen being shared? Oh, you cut out for a second. Did you say anything?
Yeah, we're ready to go. You can hear me?
Yeah, I can hear you. Okay, great.
How are we doing today?
Doing okay. So today I want to talk about the multi-grid construction for creating rhombic tilings, including the Penrose tiling. And this construction was discovered by Dugan and working with John Conway in the 70s, I believe.
Okay. The Bruin sounds like a Dutch name. Is he?
I'm not sure. Yeah, that should be a good thing to look into.
Can you pull up a browser, or let me see if I can. Actually, the Bruin, right?
The Bruin. Yeah, I'm not sure how to pronounce it.
Yeah, Dutch mathematician, it looks like.
Oh, cool.
I'm actually originally from the Netherlands, so I'm always, every time I see a Dutch name, I always want to figure out who it is. But okay, so that he's a mathematician, and he was deep. Here, I'll send a link to you in case you want to share that I'll put it on the Zoom chat.
Oh, thanks.
There we go.
Yeah, I've been to Enschede for a conference. It's really nice.
Oh, okay. To the technical university, or
yeah, Twente.
Yeah, Twente. Yeah. Okay. Yeah, I've been there. I started in Delft actually when I started my college there. I finished in the United States, but
nice. Okay, so let's see. Let's get started. So the multi-grid. First, let me describe what a grid is. So a grid on the plane is a set of equally spaced parallel lines that are all perpendicular to the same vector, to the same direction. So in this diagram here, I have selected. So this is a pentagrid. This is for making the Penrose tiling, which is based on pentagons and pentagonal rhombuses.
So the red lines here are one grid, and this is multiple grids laid on top of each other. Is that right?
Exactly. Yeah. So this is 5 grids laid on top of each other. The grid vectors are arranged equally spaced in a circle. So this vector pointing to the bottom right is the first vector, and going counterclockwise, the other 5 grid vectors are there. And
so that's the normal, or that's the perpendicular vector to the grid lines themselves, right?
Yeah.
Okay. Yep.
And so this is a superposition of 5 grids. Each grid has the same spacing of unit length. And a certain tiling is constructed from the dual to this arrangement.
Mm-hmm.
The dual being the geometric dual, where each vertex corresponds to a two-dimensional element, corresponds to a rhombus, and the lines correspond to lines, and the areas here in the dual tiling in this grid space correspond to vertices.
Right.
And the grids can be shifted.
The red lines at the moment, you're shifting those.
Now the black trail I'll get to in a moment.
Yeah.
Okay, so now what I'm doing with this point, there's a point here, a little point, and it has a coordinate list right next to it, indicating which of the spaces. Okay, so the grid lines are numbered by the dot product with the grid vector. Basically, you have one at 0 and -1. They're sequenced by the integers, and
so you just moved over one of the grid lines, and it looks like the number 1 changed to number 2. Is that right?
Right. Okay. Yeah. So yeah, the first coordinate is its coordinate along the first grid line.
Yeah. So that's a 0 now, the first coordinate, and then you go into this. You go past that red line.
Now a 1. Here, I'll zoom in some more.
1. Yep. And then if you go to the next one, it goes to 2 and then 3.
Yeah.
Let's try that out.
So its coordinate is changing as it moves past these lines, and as it moves past the red line again, the first coordinate will change to a 2.
Okay. And the more you go sort of to the down and to the right, into the corner.
So here the first coordinate's a 3.
And if you go to the top left corner, you get
negative.
-1.
-2.
-2. -3.
-3.
There we go. Okay. Yeah. Okay. And now let's try it for the second coordinate, just to kind of, so can we make the right next to, yeah. Okay. So now we're looking at
the second we're in the second coordinate. Right now it's a 1, which means we're in the first slab in this direction. And then we go over to now it's a 2. So we're in the second slab over. And now it's 3. So 3, 2, 1, 0, -1.
So every point in this plane has a unique like vector of 5 indices. Is that right? Is it unique, or can you have?
Well, so in each little region of area that's carved out by these lines, in between the lines is places where all the coordinates are the same. And
but if I like, for example, right now on the screen there's 0, 1, 1, 0, 0. There is no other place on the plane where that combination is where you can run into the same coordinates. Is that right?
Since no, there are. So everything in this like little triangle here, this little
no, I understand that. Yeah, like if you stay within the area, it's the same.
Yeah.
But if you cross any line, right? Yeah. You're never ever going to go back to 0, 1, 1, 0, 0, right?
Right.
Yeah.
Oh, yeah, I see that coordinate is never replicated in any other patch. Yeah, correct.
So it's unique. Yeah. Okay.
Yeah. And each one of these integer coordinate lists gets mapped to a vertex in the tiling by adding those grid vectors by those amounts, by those multiples. So for instance, this 0, 1, 1, 0, 0, when you follow the one of the second coordinate vectors plus one of the third.
The first one is the one that pointed down and to the right? That's where we start counting.
Yeah.
Grid, yeah, that's the one that points to the bottom right corner. Okay, and then it goes clockwise. So the first one is.
So the first one is to the bottom right, and then the second one is pointing this way, and then the third one is pointing that way.
Yeah, so it goes counterclockwise, starting with the one that kind of points to the bottom right. Okay, got it.
Right. So here we'll see what happens when I add one of these, the vector number 3, grid vector number 3. I cross this line, the third coordinate will go up, and so this point should translate another copy of this red vector, like that.
Yep. Okay, got it. Yep, that makes sense. And is there a place where it's all 0? Is that sort of it? Like there must be somewhere where it's. See if we can find it. That's all ones. Okay, that's interesting.
Yeah, that is interesting. Let's see. Oh, I guess it's.
It's hard to find 0. Oh, now we're very close. Okay. So where's your point? Oh, it's kind of
near the origin.
Okay.
And
okay.
Yeah.
You kind of shifted all the grid so they're not stuck on top of the origin.
Yeah. I had to mess with the shift back, the shifts. I have to shift the grids around to make that happen. Basically, I guess what was happening was the 0 strips on each grid were disjoint from each other mutually. So they never intersect at the same place. So I had to move them so that they all did that.
Yep. Gotcha.
And then, so moving from any of those things out, I'll get you to these vertices. Okay, so this is all the vertices that are implicit, that are derived from this configuration of grids. And now let's look at four vertices at a time. So I'll move all of these to the same patch, and they all go to the same point.
Yep.
Now if I go to this intersection, let's see, plot range.
All right, so you put one little original point in each place. Okay.
Yeah, so so the moral of the story is that the grid line intersections correspond somehow to a whole rhombic tile in tile space.
Yeah, I mean, you sort of have a rhombic thing on the screen there.
Yeah, so the meeting of the two lines is the 4 points that I'm selecting for are kind of on the four sides of this intersection.
Yeah,
and they make their own rhombus.
And right now you're putting them close together, but they don't have to be, in the sense that as long as they don't cross any lines, they're good to go.
Yeah. So I'm just spacing them out so that their integer coordinates can be seen in the plot.
Yeah.
Okay, so I'm going to zoom out so that we can see where those four vertices are located.
They all share a lot of, the beginning is shared, right? The first 1, 2, 3, 4 arrows are shared. Vectors are shared.
Yeah.
Okay. But then things go different.
Right. So let me put them all at the same point, and then this one goes that way. This one goes that way, and then this one goes
top one.
Yeah, it goes up and then to the right.
Yeah. And then those four big dots form a rhombus, right?
They form a
Like a correct?
rhombus, yeah. Because they're made of this, they're made of two grid vectors.
Yep. True. Are you frozen?
Grid vector 3 is one of the crossings, and then grid vector number 5. So they should agree on grids 1, 2, and 4. So that is yeah, so their first coordinate's always 1. Their second coordinate's always 2.
Yep.
And their fourth coordinate's always 0. And they differ on the
third,
2, 2, 1, 1, and the fifth, -1, 0, -1, 0.
Yeah. Gotcha. Okay.
Mm-hmm.
And so the fact that so the dual sort of like that projection onto the other points, is that like, why is that symmetric? Do you know? Like, is that kind
What's symmetric?
There's a certain symmetry to those, right? The larger points, the dual points, right? That's because we're using those vectors or something that's sort of kind of guaranteed to be symmetric.
Yeah. So since you can start from like the lower corner here and and know that it's gonna just be a rhombus by construction around an intersection of grid lines.
Yeah.
Okay. So, and then that happens around every grid line intersection. So here's another rhombic tile.
Yeah. Okay. They take different paths, but it's, yeah. Okay. But every rhombic every sort of, you know, we're calling it a rhombus, right? The four big points. If you have to kind of think about that, you're connecting those with a line, right? I think we'll see that in a little bit, but they're unique in a sense, right? I mean, just like those coordinates are always unique.
Yeah.
Those rhombuses are also in a unique place on the plane.
Yeah, each grid line intersection corresponds to a unique tile.
Yeah.
In the plane, and there's no 2-to-1 on that.
Yeah. Okay.
So let's with the grid of if you shift some grids around, so if you shift this red grid past this grid line intersection for the other grids, the gray grid, it'll scoot the tile that is corresponding here over exactly one of those red grid vectors. So you can effectively translate the tiles by shifting it one grid value, and it would sort of modulate the whole tiling when you look at it.
Oh yeah, I see that. Right.
And there's a slight permutation that happens during the event. That is, well, one is like cutting in between those four guys. You get some jostling. Some other tiles are happening elsewhere, but when it's all said and done, then you have the whole tile just translated in place.
So by moving those shifts around, that's one way to get the multiple.
Oh yeah,
I guess tiles. Yeah.
Let's see what happens. Yeah.
Oh yeah. Yeah. not instantaneous, but that's just because that one of those red lines has to cross all four of those little dots, basically. Yeah.
Yeah. Here we can really see the lines pushing that.
Yeah.
Okay.
Oh yeah, I see that. Yeah.
So that's a little taste of how the dual system works from the grid. The grid's equally spaced with the condition that no three lines intersect at the same place.
Mm-hmm. Mm-hmm. Yeah.
So that each intersection has four areas around it in a quadrilateral sort of way.
Yeah.
So that precludes, for instance, having all the grids at zero.
Yeah, you don't want that because then that system is going to fall flat, basically. You cannot, then there's places where you cannot put all the little dots around the intersection anymore necessarily.
Yeah.
Okay.
Mm-hmm.
So let's go into the tilings here. What are we looking at here with the tilings?
So these are the tile types for arrangement, a pentagrid, 5 grid.
So that any combination of those 5, like 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, like that basically, or?
Yeah. Okay. 1, 2, 1, 3, 1, 4. And then, so there are 10 of these combinations.
But let's, hold on, let me make sure. It's 1, 2, right? And 1, 3, 1, 4, 1, 5. That's 4 of them, right? If I'm counting correctly. Okay, there we go. Okay, that's 10. And that's just, okay, 2, 3, 2, 4, 2, 5. 3, 4, 3, 5. Okay, so no repeated, no 1, 1s, for example, and also not once you've covered 2, 3, that's the same as 3, 2. Is that like, and in the Wolfram language, how do you construct that list? Is it some sort of tuples command or subsets? Okay. Range 5, 2.
Oops.
Oops.
There we go. Yeah.
So that's range 5 is just 1, 2, 3, 4, 5, and then you're just picking out combinations of 2 of them, and then I guess subsets is sort of deleting all the possible duplicates.
Yeah, so it's they're ordered. And so there are just 10 of them. And so 5 of them. So it's these rhombuses made out of pairs of the grid vectors as sides. And you can read off the area of each one using the determinant of the matrix formed by those 2 grid vectors.
Can we do one simple example of that? Like take, I guess, when you go back to circle points or whatever. Yeah, let's see. And 0, 0 is the starting point, and then so parallelogram is just a parallelogram that starts at 0, 0, and then goes in those 2 directions. Is that right? Or
yeah. Why did that work?
I'm not sure. It's a parallelogram. Like, what's the syntax for parallelogram? I'm not sure.
There we go.
So what's tile type grid vectors of 1? What does it look like? Is that?
I think those are the pairs of grid vectors for each tile type. Okay, yeah. So this is grid vector 1 paired with grid vector 2.
Okay.
And then
you can use area to compute the area there. If you just say parallelogram of area.
Yeah.
Okay. Gotcha. Okay.
And that should be equal to the determinant.
If you do the determinant of those things, then
Yeah.
oh yeah. Okay. Well, I
Mhm.
guess that's nice. Nice. But that's yeah. Areas, of course, not always. Okay. I got it.
Yeah,
It's
it's not
just
always
because it's
so
a
easy.
parallelogram.
Yeah.
Yeah.
Since it's a parallelogram, you could just, you know, that the
Yeah.
just feed those vectors into the thing.
Gotcha.
Oh,
Okay. And like later on, you're going to use the area for coloring tiles as well, I believe. So
that's
yeah.
right. That's right.
So let's like, for
But it's
example,
going to be
maybe
coded as determinant.
yeah. So show that in the maybe in the graphics there where you have graphics of parallelogram. Maybe you can put that in a list and kind of do like put the parallelogram in the list maybe. Like we're in 1163. Oh, no, sorry. Go down.
Oh, this one.
Very simply, but I kind of just want to show like if you take parallelogram and before that you do this open curly brace and then something like U or gray level.
This one.
Yeah, just do like well after the curly brace do like U or gray level, doesn't really matter, like just some sort of color function there.
Oh, I see. Like,
Yeah. And then face form of gray level could be I might do like gray level of the determinant of that thing that you had.
oh yeah. Okay.
Like you had some computation with where it says det of, yeah. Okay, there we go. So that's very light because we have 0.95 in gray level. That's almost one. Like gray level 1 is white. So if you have, yeah, okay, this is a smaller area, presumably, and it's slightly darker gray. Okay. Yeah, that's kind of what I wanted to show. Okay.
Okay.
Because yeah, you're going to use that here basically. So okay.
Yeah. So here I made a function that helps me do the plot. And it's does a lot of linear algebra.
Just puts it all together, right? Like this is like every one of those little, yeah, every one of those little rhombuses is a right, was constructed with that method you showed earlier. Yeah. Sorry, go ahead.
Yeah. So you would go to the would go to each intersection for grid lines and compute the tiling, the tile associated to it, the rhombus.
Right. So you systematically find those intersection points somehow.
Yeah. And once those are, then you so the intersection you say, okay, I need grid vector 1, slab number A to intersect, grid number J at slab number K, whatever. And then you would read off the other 3 coordinates that belong to the other 3 grid vectors. And then then you would add 1 for each of the grid vectors that you care about to make the rhombus.
Right.
Effectively sampling somewhere these 4 points nearby.
Yeah.
And it plots all the tiles and it colors them by their area.
So there's only two colors here. There's the sort of the gray level that was 0.95, that's almost white, and the other one that's I guess closer to I don't know 0.3 or 0.4 or something like that. So there's 2 colors going on here.
Yeah.
Yeah.
So for the Penrose tiling, the classic tiling here, it's you want grid values of 0.2. And
is the 0.2 significant, or is that just a nice value for generating stuff?
It's significant because it changes the characteristic of the tiling.
You're going to use 0.1. Okay.
So here's what happens if I break the rules and I put everything at 0. You get
doesn't look
some jumbling up here in the middle.
Yeah. But if you do like 0.1 or something, or
here are all the so you have to kind of offset it at least a little bit.
I see.
Here I'm expanding the grid range. All right.
You get just different types of grids every time.
Yeah, you get different vertex configurations exhibited. So here the 10 small rhombuses all around a point, that's not found in the Penrose as according to the matching rules of the Penrose tiling. So this has a very different characteristic than this one.
Now, are these like regular repeated grids, or is this already?
So this is the pentagrid with various different shift values.
Okay.
But
if you go up more and more out, I'm sorry.
These so expanding out words, it's still an aperiodic. These are all aperiodic tilings.
Right. That's what I was trying to get to. Yeah.
Even though there are features which are similar, but if you expand out around it, you'll never find the same. You'll never find a translational symmetry for the whole tiling.
You cannot pick it up and just lay it, shift it around and then lay it on top of itself. Is that okay?
You can find local correspondences, but those local correspondences don't expand out forever. So you can find like the circle of these circular, the 10 rhombuses around a vertex. You can find those vertex arrangements, and then if you look for more symmetric arrangements like this wider circle around that, you can find instances of that, but they're more spread out from each other, because they're a bigger patch.
So you can have small patches matching translationally, but not the whole thing. Like normally when you have it like a tile, right? Like a square tiling, right? You can lift it up and shift it over, and it fits onto itself. But that's not the case here.
Right. There's no direct translational symmetry for these tilings. They're aperiodic in that sense. However, under certain shift values, certain parameters, you can still have it be the case that it's rotationally symmetric around the origin. And so that there are at most one point of rotational symmetry. For the whole tiling.
So this one may be rotationally symmetric if you look at the very center and you start rotating it.
Yeah. In fact, the shift values being equal enforces a symmetric arrangement in the grid space.
Oh, I see. Okay.
So if the grid has radial symmetry, then so will the tiling.
And if you make one of them different, like can we do something like all 0.1s, but 1 point, that has like 0.2 or something, or
yeah. So I have a
oh, there's one. Okay.
Yeah, there's an example. Well, I guess 2 are shifted from the mean. It's kind of random. Here's another symmetric one, 0.25. Let's see, I have a manipulate that does good things. Here we go.
So these have the Y1, 2, 3, 4, and 5. That's the shift, the grid shifts, basically. Okay.
Yeah, so here's the effect of shifting one grid at a time. And here's the effect of changing all the grids together to move to different tiling types.
Not sure I understand that. What does tiling parameter do here? Is that sort of the base value or something, or?
Yeah, so here I'm kind of cheating a little bit. So I have the grid shifts, and then I have a tiling parameter which adjusts all of them equally so that their mean comes out to be the same value. As tiling parameter dictates an adjustment for the grid shifts.
Okay, it's just shifting all the grids together.
Yeah,
that's a global parameter, and the Y1, etc., is a sort of a tweaking of values.
Yeah, so there's some, yeah. And so if I modify this value, it preserves a certain characteristic in the tiling. Such that like when I say characteristic, I mean like the areas, they kind of have these triangular areas for this one, let's say, of more or less dark tile. I don't know if that's visible.
Okay, yeah. So you're increasing the contrast here.
Yeah. So I want to say that like in this area is lighter than that area. And the amount by which and then and the let's see, there's a sweet spot here where it evens out. There it is.
Oh, I see. Yeah. Okay. So that's a very evenly spaced coloring. So that the parameters.
So this is the evenly spaced sort of Penrose tiling, and then deviations from that kind of carve that space into homogeneous regions, and then you start getting these vertex types here, and then I want to say that let's see. For some values of the tiling parameter, there's a greater concentration of these little rosettes.
Right, I got that.
And changing the shift values here in this way just kind of permutes the tiling, but preserves the amount of that vertex type, preserves the vertex, preserves the tiling class or the tiling structure of it.
Yeah.
So here everything's more spread out.
Yeah.
Okay. Now I want to, let's see. This is a tool for looking at rhombic rosettes and looking at the dual together with the tiling itself, kind of in the same plot as a.
Are we going up to a higher number of grids? This is more than 5, right? We're switching from grids or 5 grids to well, I don't know how to count them. Is there a number somewhere to find what's
all up here?
21, the very top. Okay, so We're going from 5.
Okay. Yeah.
That's 5. Yeah, and that's
All right. Start with a pentagrid here.
so what do we got here?
If I can increase the probably not.
Let's start with the first, the thing above it, right? That's the 2 possible
Yeah,
shapes.
so these
Is
are
that right?
tile types by size.
Yeah. Tile types is just, they just look like it. They may be rotated in some orientation, but they're essentially the same shape. Is that right?
Yeah. So I deduplicated that list by just their area.
Yeah.
Or their equivalently here, their angle.
Yep.
I guess I have tile angles listed. Now let me go to something more complicated. Yeah, so here I have 10 grids. Anytime 2 grid lines meet, there's a tile that's formed, a rhombic tile that's formed dual to it. And here you can see that the edges of the rhombuses are perpendicular to the grid lines that run through them.
Yeah.
And
but in this case, you're also scaling, right, to get those rhombuses kind of to sit on the grid lines. Is that right?
Yeah. So here I have a bunch of grid line intersections all next to each other, and I have a tile, and they should be all the same size. But if you make them all the same size, they start bumping into each other. So overlapping each other.
Okay.
So in this visualization, I scaled each rhombus based on how close its nearest neighbors are and told it not to go larger than that.
Right.
So here you can see all the grid line intersections with their corresponding rhombuses scaled so that everything is visible. And if you imagine making the rhombuses the same size and then gluing edges together that are adjacent along edges, that is along grid lines. So this white grid line here binds the bottom face of this blue one with the upper face of this green one. So if you take those tiles and you obey those connections, you'll get this out.
Okay, you can morph them into each other.
Right.
Okay.
So this is a visualization from the grid line intersections to the tiling that's generated by them. And here I'm going to change the grid lines so that they're in a different arrangement.
And just the amplitude phase and etc. That's just that had to do with the how do I say that, the shifts, right? Like in this case, you're sort of doing a do you have that visualized somewhere? I think last week you had that. Yeah, okay, there we go. Okay. Is that the
Let me bring that up top. Okay, so there's want to wait. The plot and the graphics. Okay, so we have the grid lines. Okay, here are the grid values that I'm using.
the grid shifts.
The red points. They're all at whatever they're at.
They're the same right now.
Yeah. So here is by push them all out together, push them all in together. That's what this gamma offset is. The vector is called gamma in the literature. So that's why the gamma shows up. Okay.
Yep.
So if I change the grid values, so here I'm oscillating them. There are 10 of them. I'm pushing some of them, 5 of them up more than 5 of them down in an alternating fashion.
Right.
And you can see that in the grid here with these red lines. Each red line corresponds to one of these red points. The longer lines correspond to points that are further up the axis, the y-axis. So the grid shift values are exhibited here.
Yeah.
And pushing grid lines past each other will change the arrangement.
Right.
So in the first arrangement, the green tiles are at the center. And here I push things around so that these blue tiles are there at the center. Okay. So changing the grids will affect discrete changes in the tiling. And so long as, let's say, the grid values have a symmetric arrangement, then the tiling will also exhibit some sort of symmetry. So here, no matter what I do, if I modulate the grid values according to this sinusoid that has a periodicity 5, and there are 10 grids, then I can maintain 5-fold rotational symmetry in the tiling. And since this is a sinusoid, I can phase it.
Yeah, like shift it to the left and the right.
Now I'm going to increase the number of grids I have. Let's go to 15.
Now you have 7 different tile types.
Yeah. 7 different tile types by area. And there are a lot more grid line intersections here, and there are a lot more tiles.
Yeah. And so this is, so what was the number 15, right? That's what you used. And if you morph the bottom slider there all the way to the right, it's
yeah. So here I'm, so there are 15 grids, and with the periodicity of 5, you get sort of 3 values repeating on the grid values.
It's high, low, low, high, low, low. Yeah,
exactly. And this is the rosette here at the center.
So we have 5 plus 5 is 10. So 10 around the center. Yeah. And is that bottom picture, is that just a particular, that's sort of the center of a larger thing you can make? This is sort of the, you can extend this plot in principle, right?
Yeah.
Okay. This just happens to be the very center of it.
Exactly.
Okay.
So yeah, there's a tiling that goes beyond this little disc and fills the whole plane aperiodically with rhombic tiles. So it's going to be like a Penrose tiling, but just on steroids, just more.
Right.
And And so with certain constraints with the grid, yeah, so the inside this disk, this rosette, these tiles are being permuted in their place.
Mm-hmm.
So it's the same tiling set. That's interesting.
Yeah, when you say tiling sets, you mean the same
The same
number of
set of
each
tiles.
tiles. Okay.
So like you can get like a laser cutter, cut all these tiles out, and then
Yeah.
um,
Just
in a
rearrange them.
symmetric way, you can arrange them like this.
Yeah.
And these types of rhombic rosettes are well known. You just start with the thinnest tiles at the center, then progressively
Yeah.
go like that, and then you get everything arranged in a perfect n-gon around its perimeter.
Mm-hmm. A little bit like a sunflower idea almost.
So increasing the amplitude slightly along this sinusoid for the grid shift values changes the tiling so as to permute the tiles starting in the center a little bit. So
Mm-hmm.
some of these green tiles kind of get shifted out. And they trade places
Yeah.
with some of these turquoise ones.
Right. Yeah.
And then being able to phase that. Phasing the sinusoid means I get to sort of have a one parameter family of tilings that repeat.
Mm-hmm.
So you can see that kind of that pentagon inside there rotating in place in kind of a discrete way. And for the dual, it's kind of fun to watch the grid lines wiggle about.
That's pretty cool.
And so the more the variance in this grid, in these grid values, the more the perturbation around the center.
Mm-hmm.
And even to, affecting the outer rim quite a bit.
What's the maximum number of possibilities, or what's the total number of possibilities? I mean, there must be, since there's a finite number of tiles with a finite number of rearrangements, so there must be some number here. Is that easy to compute, or is it just like?
I don't know. Yeah, it'd be combinatorically probably explosive. I would imagine it'd be pretty high, but it's probably possible to compute. I'm sure.
Yeah, I mean, there's, I don't know, like I'm guessing like 50 or 60 or so tiles we're looking at. Not sure.
So the number is 15. So if I select for a three periodicity sinusoid, then I get a tiling with threefold rotational symmetry.
Mm-hmm.
And so that's I can select for that.
Yeah.
And then I get like a little 3-leaf rosette spinning in the center instead of a 5-leaf rosette.
You can get it's 15, so 3 times 5, right? That's the symmetries you can get out of this. Presumably, you cannot get a 7 symmetry out of this thing.
Exactly. So if I go up and then I change this tile count.
Two different prime numbers, like 3 times 7 or something, or yeah.
Yeah.
But that's what you had initially. You had 21. Okay.
So now I can go
almost.
So here you can kind of see that it's trying to push some sort of 5-period rosette onto the 7 periodic thing, 21 grid. And now with a 7 periodic sinusoid dictating the grid shift values, we get the 7-fold periodic rosette.
Yeah.
And let's just change the amplitude, pushes the everything out to the edge, and lowering the amplitude brings everything out to the center. So yeah, here, keep going. Outside of that rosette, the tiling keeps going.
The rosette ends where exactly? Sort of the core one?
There it is. Okay, yep. So when the grid values are very, very close to 0, you get a rosette in the center.
Okay, I see.
And I've been cheating here because I want to say I've multiplied the grid vector by something very small. Maybe.
To force the rosette thing.
What? Yeah.
Okay.
Okay, well, more on that later, I guess. So the, let's see.
Now we're getting more sort of, now we're getting a little bit more in the art of the deal, right? Like we've covered the basics of the basic ideas, and this is,
And this is really fun. So here I'm changing the tile color function option for this little function I wrote. Basically just maps the tile area to some gradient that you choose. So red blue tone seems to be pretty good.
So just try a different one just to kind of show what, like if you change red blue tones to something else, like
rainbow.
Yeah, gotcha. Okay, so that's just a gradient from 0 to 1 or something. Oops, no, it's not alpine. Yeah.
Alpine, yeah.
Okay. And you're scaling the tiles again, like if a tile is area 1 or something, then it's at the top of the color scale, and 0 is at the bottom of the color scaling. Okay.
So all the tile areas are pre-computed, and then you get a color gradient going from the min to the max, basically.
Mm-hmm.
Is that those tile values are rescaled from 0 to 1. And then
Okay, so like the smallest tile could be like 0.2 and the biggest tile could be 1.5 or something, but you rescale it to go from 0 to 1. Okay.
Yeah.
Okay.
So you increase the grid count,
Mm-hmm.
get more and more symmetric things. So let's see what happens when there we go. With the random grid amount, that tiling of the rosette at the center disintegrates, and those tiles go flying out elsewhere. So the integrity of that rim breaks down if the grid value is allowed to get too big, essentially, or go outside of some sort of convex parameter space.
Right, you lose all sorts of symmetry. This is with the shifts, right? This is a 40 grids, is that right? 40 grids, and then the sort of random shifts. Is that the idea there?
Yeah.
Okay.
No, there's a 15 grid.
Apparently. 15, okay. 15, and then
yeah. Let's see. No, I guess it's still a 40 grid. Yeah, it's a 40 grid.
Okay. I'm just saying that because that plot goes to 40. So
but no matter what that grid, what those grid values are, if you scale it down, it'll pull that grid vector into its the region which preserves the perfect n-gon.
Nice. So you could make an animation, right? You can make an where you start with a really small, right? Almost close to 0, and then you go up, and that sort of explodes into. Okay. That would be an interesting animation.
And here's something interesting. Okay. For a given shift vector, a list of shift values, depending on how much you, let's see, scale it.
What are we trying to do?
I'm just going to show what happens with the scale vector, the scale value.
I see.
Oops.
There's a implicit multiplication somewhere that you probably don't want to have. You got that list line.
Yeah. Let's see. There.
There. I see. That's an animation of moon.
Yeah, so it's chipping away at it, and then it disintegrates. So what's interesting is that there's that there's a radius of convergence.
Mm-hmm.
And there's something interesting that happens to the rest of the tiling at the same time. Okay, yeah. Whoops.
You just change the grid range so that now it includes more. You set it from 0 to 1, so now it includes a lot more. Yeah.
So the shape of the grid values is staying the same. It's just they're all being scaled down to 0. And there's sort of a central configuration that gets solidified. So there's like a tiling as you approach 0, essentially, that includes the shape inside the rosette and everything outside of it.
Yeah. I kind of like when you go up in value, that the chaoticness of the that's kind of neat. Especially like outside the rosette, it's that's very well. Okay, there's some.
And so what's interesting is that in all these cases, the perturbations inside the rosette are manufactured outside the rosette. But what this scaling of the shift values does is move those perturbations inward. So you can see how like you have these like rows coming out in pairs here, but here there's like a kink in this one.
Yeah.
And then over here, there's a kink there too.
Yeah.
And so that corresponds to like this, something that's happening here is happening here on the outside of this inverted around about the circle.
Can you do on the graphics thing, can you do axis goes to true? I'm kind of curious what the scale of the thing is that I'm looking at.
Oh yeah, this is a plot range 40. So
yeah, but
okay,
can you show me the axis? Just to kind of, I know it's going to look ugly, but it's going to just after.
I don't think
easy to do. Oh, you cannot do that. Doesn't.
Yeah.
That's not going to fly. Okay.
Let's see.
It doesn't pass in the options. It doesn't pass along the options, I guess. That's fine. But if it's hard to do, then don't worry about it.
I don't know if I'm overriding them. There we go.
Oh, there you go. That works. Okay. All right. So that's the scale of the X and Y axis we're looking at, basically. Okay, gotcha. Okay, you can undo that. This could be distracting. I think you said it's very globally at the graphics object itself. So.
Oh yeah, the option.
I think the axis goes to automatic or in it. I think it's automatic. I hope. Or false, whatever. I don't want to mess you up. Like.
Let's do that. There we go. Okay. Yeah. So yeah. So let's see. I went over the variance and the scale. Make it really small, like 0.02 to 0.01. You have it vary between that range. You're gonna have rosette that's perturbated more towards the center and it's more symmetric. In the sense that it's more, the rim of it is unperturbed, but only the center is. This was a fun experiment. You get some really nice rosettes when you just kind of repeat a certain chosen value
Mhm.
a bunch of times. Yeah. And this is detailing how I use a sinusoid to phase it.
Yeah.
And that hopefully makes an animation. Let's see. There we go.
Now you're changing one parameter here. What's the parameter that changes here?
So I'm changing a phase value here that makes this 7 periodic or 14 periodic sinusoid.
Mm-hmm. Okay.
And I'm phasing it 1/7 of it, or however I'm phasing it, it's coming around to the same point at the end that it does at the beginning, so I can loop this GIF.
Yeah.
And make an animation.
Yep.
So that's the magic sauce on that. And here's one where I'm modulating the grid vector scaling, where it's allowed to perturb almost to the rim of the end god, but not quite.
Mm-hmm.
And this plot is also showing a little bit of the tiling around it. And what's fun is you can kind of see let me get see this pen, I think. Yeah, here we go.
It's just same. It's a similar thing, but turned into an MP4, right?
Yeah. So here I rendered out a bunch of still images and made a movie out of them. And you can kind of see around the tiling, these little bends and kinks that are traveling in a clockwise manner
Mm-hmm.
around the rim.
Yeah.
So yes, it's showing how the tiling outside the rim reflects the tiling inside the rim.
Yeah. It's almost like there's 3 regions. There's the inner center circular, disk area, and then there's a transition, and then on the outside there's kind of looks like a little bit Escher-ish cubes.
Yeah.
Okay.
Well, someone commented like, "Oh, is that like Escher?" Because it looks like some of those hyperbolic drawings where the things on the rim get really small.
Yeah. But the
This is
color
not
scheme is
that,
also
of course, but what is true is that around the rim of the rosette are small polygons.
yeah.
It looks the same. And then here's the one, the red one. So this is a 7-fold periodistic, has 7-fold rotational symmetry, and it's trying to rotate 1/7 of a turn every 10 seconds.
Yeah.
What I like looking at is around the perimeter, you can kind of see the individual swaps of the tiles as they move past each other, especially the really thin dark ones. I kind of watch them fall and rise as the petals of the rosette move past it.
It's amazing that they fit when they swap. Yes, would not expect necessarily for that all perfectly fit, but I guess it does.
Yeah, it's let's see. I made some other ones that are showing how the tiles are sort of swapping place next to each other all the time. And it's sort of getting permuted.
Yeah.
This is showing, keeping the perturbation tight around the center and circling that. So this is just showing inside the rosette, growing and shrinking.
Mm-hmm.
And this is, I wanted to emphasize that it's a completely symmetric rosette. All the tiles are there, but they're just being permuted.
Mm-hmm.
And this is the same thing starting. So starting with a perfectly symmetric tiling, and then adding some sevenfold perturbations to that.
Mm-hmm.
These are just more of the same. Okay, here's where I allowed the tiling to disintegrate along the perimeter of the circle. Oops. So what's happening here is started with a rosette, threefold symmetry. And the shift vectors are large enough that
start to expand out.
Yeah. Okay, so here you can see the red tiles of the perimeter start to get pushed out, so that they're not there anymore. And then there's sort of this harmonic and the shift values. I'm not sure like why it's there, but you kind of get this doubling effect where all these tiles are the same size or next to each other. So I want to say that that probably indicates that the number of grids is even. I could be wrong about that. I forgot what it is for this one. And then now we're back to the original harmonic. I say harmonic when what I mean by that is that there's implicitly going to be, if I kept going, there'd be a larger ring that's like double the size, I think.
Mm-hmm.
I think that's the same one. This one operates a bit slower. It only Yeah, it's rotating slower, more slowly. It's more visible.
Can I
Yes,
try a
that's
few?
fun.
Yeah, it is. I think I want to try a few cases. Is that, how do I see? I have the notebook right somewhere.
Mhm.
I should have the notebook.
Do you want the screen?
Hang on, let me first get the. I can figure out where my notebook is. I think I downloaded it. I mean, I have the same notebook that you sent.
Yeah.
Okay, yeah, I think I can share now. I just hope it doesn't. Well, it should be okay. I'll take out sharing.
I'll. Oh.
You see my screen, or?
Yeah, I can see your screen.
Okay, all right. So let's see. We covered all this right here.
You might want to evaluate the init cells and all that.
Yeah. I'm missing something.
Oh no. Oh, I sent you an updated thing on the Discord.
Oh, okay, let me try to get that. I thought that's it.
I it's the latest one.
I think so.
Here.
_2. So, well, I mean, I can take the.
That's the most recent one. I sent you two of the same file name.
Oh, I see.
I think. There
Oh, I
should be
see.
a difference.
Okay, yeah, there's a much bigger one. Okay, let me
Yeah,
try
yeah,
that
yeah.
as well. Okay. That's probably better. Yeah. I'll do it in a new notebook. I think mostly I want to get, this is the core thing, right? This is
Yeah.
the one that's that's the one that's fun to play with.
Uh-huh.
I should probably just mention also the,
Oh yeah, this is
you wrote up a lot of stuff on community. So maybe that's good to mention here if I can. I'll put that in the Twitch chat for people.
yeah,
We probably
those
should have
links
mentioned it at the beginning.
yeah, these are available online at the Wolfram community.
Okay, find that.
Just for Penrose tiling.
Yeah.
There we go.
This is you. Let me put that in the chat for Twitch if I can. No, I can't. Hang on a second. I have to do that differently. Sorry, I'm on multiple computers here.
Yeah.
Oh, here we go. The people that are watching it live or people that are watching it in the future, I'll put a link on the Twitch chat. And then this was the original one, I think, 2 weeks ago. Yeah. Anyway, you can find it from there. So let's play around a little bit with these.
Yeah.
So this takes one argument, is that right? This takes
Yeah, one argument. Just a list of values.
okay. Can I start even with like 3 or something, or is that
Yeah.
what's the smallest you can do here? Okay, that works.
Uh-huh.
So this is what about 2? Like how low can you go here before it starts to okay, that doesn't work. 3 is the minimum here. Okay, I guess that makes sense. And then you can also what happens if you do 4? Is it just going to be like okay? Those are actually interesting. And if you make those,
Yeah. So
no, that doesn't make a difference here.
yeah, for like a form grid, yeah, because that wouldn't the dual would always be the same. It'd just be like these no matter you just have like a rectangular grid of some size. So you have all these rectangles, and the dual of that topologically, it's just a square grid. So yeah, for some of these are trivial. For
Okay, so
3,
that's it's just not interesting until you go to 5, I guess. Okay,
right.
That's 5. Now, what if I just do something like random real of
Yeah.
no.
Yeah, 0 to 1.
So 0. This is 0 to 1, and then 5.
Yeah.
Okay. And if I want to have a little bit bigger, okay, that's the grid range option here.
Yeah.
Grid range goes to 10. Okay. And then you can also set the plot range, right? To kind of clip it. Okay, there we go. It's kind of like what okay, this is, yep. These you have to kind of tweak together if you want to don't get white space, basically. Okay, there we
go. Yeah.
Just the very edges are, okay. So how high can you go before it starts to fall over? It's just.
For higher numbers, you'd want to set the grid range down a couple notches. You might not want to do that. Oh boy, the 80 is a lot.
That's bad. Okay.
Yeah, I might want to abort that.
Okay.
Oh, it went.
Nice.
It went. Look at
that. See, I kind of like
all
those
over the place.
Yeah, chaotic things. It
takes
a little bit longer. But...
Bring the grid range down.
Oh, the grid range. Okay. That's I like that.
Yeah.
But okay, but it's it's a lot of that's just it's even slow to render. So okay, maybe that's probably okay. Let me delete that. Okay, that's at the very edge of what it can do. You're saying bring this down a little bit. Yeah. Okay, let's and make this smaller. Is that what you also said? Okay.
Yeah.
Okay. Now we got that circle again.
Yeah. So you reduce the size of the grid shifts. So you're preserving the integrity of that n-gon, whatever is going on in there, is going on outside with the yeah.
But that goes away the moment you start blowing it up, right? If I do, when you start increasing this, at some point it's going to go away, I think.
Yeah. It's already starting to deteriorate. There you go.
Yeah, now it's pretty much gone.
Ooh.
Yeah, there's still something there. Can I give this an image size option, or is that?
Yeah, there's an image size. I should I should find a way to just however filter options for whatever things you get.
Yeah, you can do options pattern, I think, if you look into that.
Yeah, it's already It's already doing that.
Oh, it's already.
I'm already using option pattern for that.
Okay. Then it's just a matter of passing along the.
Yeah. I haven't read the code to pass that. Ooh, that's gonna be huge. Oh, I see. Oh, that's the size of its full. Got it.
Full is to the side of the notebook, yeah. So
yeah, so 40 is still 40 is computable. 20. Now get the ring back. Set the
by lowering this, you mean?
Yeah.
Yeah. And then set symmetry. And you can also pick a color thing, right? Tile color function.
Yeah.
And I can pick any color data thing as long as it's
color data. Choose a
choose color scheme. Okay. It's one of my favorite.
That's a good one. Yeah.
So when you make animations, I guess when you make animations with make multigrid tiling plots, I guess you're just mostly tinkering with these settings, right? Like you start with this particular starting point, like Q is like well, can be anything, but like that, and then you possibly like start changing values, I think.
Yeah. So I have, some sinusoid function set up, and I phase that. I sample the grid values based on interpolating that sine value, that sine curve.
Yeah.
And then I make adjustments for how much I want the variance and how much I want it scaled, the values, and then so that gives me control on, the symmetry and the if I want a rosette at the center, that kind of thing.
Yeah.
Now, what's interesting is that these tilings get like really aperiodic in the sense that the rosette at the center as a patch of tiles, that's repeated at various points in this big tiling that's a mess everywhere that goes out forever. But the locations of them are going to be very, very sparse.
I see. Okay. So somewhere this is repeated.
Yeah.
An infinite number of times, even?
An infinite number of times. Every configuration exhibited in the tile is repeated an infinite number of times in the tiling.
Yeah.
And the bigger the patch, the rarer or the more spaced out these things get.
And is that computable where they're going to pop up, or is it sort of like that's just super complicated?
Yeah, it's computable. It's difficult.
Okay.
But it's computable.
I can imagine.
Basically, yeah, it's like there's a lot of convex geometry. A lot of and
I could do let's see. If I just wanted to see the grid range, you can start at 0. Okay, 0, 1. Okay, so you can make a table of that, right?
Yeah. Grid range.
0 to 10, maybe. Let's try that. Yeah.
So that's filling up.
Yeah.
And you can kind of see these lines extending out.
I see that, yeah.
And that's interesting.
Like at frame 8 or 9 or something. It does that.
Yeah. So here's something interesting is the Penrose tiling being a pentagrid. And remember when we had we were dragging that point around and it was giving a 5 integer coordinate list.
Yeah.
So that's a coordinate in the Z5 lattice. So it turns out that the Penrose tiling is a orthogonal projection of a selection of Z5 vertices in 5 space, projecting onto a 2-dimensional plane.
Oh, I see. So you're actually kind of looking at the shadow of a the shadow of something higher dimensional. So
Exactly.
Okay, that's kind of cool actually. And that's
even
even the case here as well.
Yeah, I believe so. That an N grid, if it's symmetric, then it's going to be a certain projection of the Zn onto a 2-dimensional plane. For these,
so if I do, let's make that case here. Let me see if I can. Let's just go back to this single plot here. I don't know. Okay, so this is a projection of a higher. This is the shadow of something that's 21 dimensional. So that's one way of. I mean, maybe that's okay. It's kind of weird.
Yeah. So there's for a different day, but there's a different construction called the cut and project method, creating aperiodic tilings and quasicrystals. That involves going to a high dimensional lattice, a crystalline lattice, and embedding a two-dimensional subspace in that, and collecting the lattice vertices that are sufficiently close to that subspace by a certain selection criteria, and projecting those selected points that are nearby that surface onto that surface orthogonally.
Yeah.
And so long as the subspace is oriented in a way that's incommensurate with the root vectors of the lattice that you're taking a slice out of, as long as that's the case, as long as the subspace doesn't line up with the root vectors, then the tiling that's selected for is non-periodic. That is to say, if the for instance, for the Penrose tiling, the slope of that two-dimensional subspace is irrational with respect to the coordinate lattice vectors in Z5 or in R5. And changing the shift values is equivalent to translating that projection plane in 5 space.
I'm going to have to do a lot of learning to understand the sorry, that's the what I did like. There was something. Was it with 21? See, I guess you have to tinker with. Oh no, yeah, you did some. You didn't do constant there. You did something with.
Oh yeah, I repeated like some values. So
yeah. Okay, so we can just do something
constant like array 1, 2, 3, and then you repeat that a bunch of
something like that. Well, no, This table.
Yeah, just
that's
table that
7 times
and then
flatten.
flatten it. Yeah.
Okay.
There we go. And then plot range, zoom in. Yeah, see.
What am I seeing here? There should be something that's 3 times 7, right? Or
Yeah, so you see there's an undulation. It's seven going around.
let's see. 1, 2, 3, 4, 5, 6. Oh, yeah, you're right. Okay. I don't see 3 yet, but that's maybe that's just because the values I picked are not really very conducive here. Yeah, I need to switch my headset.
Yeah, so try adding an offset. So the
Still hear me? Okay. Sorry, I have to switch.
oh, there you go. Oh, I see. Yeah, you shrunk it, so now it's a perfect n-gon in the center.
And I don't want to shrink it. That's what I do. Okay. Should I make it bigger? So that's maybe oops, go away from.
Let's see what happens.
Okay.
Yeah, so it's still 7-fold periodic. The ring in the center is gone, and then it's just a nice tiling.
But maybe I should do it the other way around, like do it this way.
Oh, I see.
So
make 7, yeah. So let's see what happens.
Let's see, 1, 2, 3, 4, 5, 6, 7. But now it's the other way around. So I sort of have a. Okay, there's the 3. Okay. Sorry, that's the. Okay. It's nice to now know a little bit more about the values you can pick to kind of predict what you're getting. Okay, so this was the trick here.
Yeah.
If I make this even bigger, then it goes. Okay. The bigger this goes, the less I get the circle in the middle. But if I make it smaller,
right.
Okay, I still have the 3-fold thing.
Yeah, you still have a 3-fold perturbation, but it's more concentrated towards the center, and outside the circle, it's more diverted towards the. Yeah.
Gotcha. Okay. Well, I think I'm inspired to make some new animations now. So maybe over the weekend.
Yeah.
This was quite nice. Thank you. And I think we actually got audio recorded on the Twitch stream. So.
Oh, I hope so. Yeah.
We should probably wrap up.
Yeah.
Well, thanks so much, Dugan. That was really cool.
Oh, my pleasure, Arnaud.
I'm gonna have to make some new animations now, but this is cool. So.
Yeah, all the tools are there. I have some sampling animations that I sent you, so you can kind of tweak those, and I'd be interested to see what you come up with.
Yep. Let me see if I can stop the live stream here. So thank you for watching. If you were watching, I think we had some people watching. I'm not sure that.
Oh, that's good.
They were all talking.
Did we get any comments or anything?
I don't think so. But I think I had comments kind of restricted, so I turned it off in the middle.
Okay. That's fine.
But I'm not. Yeah. Okay. I just don't know. They made the chat a little bit more complicated than the last time I used it. So, okay, I'll stop the live.